previous physical science labs dealt with chemistry and chemical reactions. Beginning with this lab, we turn our attention to physics, the branch of science that deals with energy and how energy affects matter. In our study of physics, we will look at the following topics: mechanics, electricity, optics, electronics, and nuclear physics. During this lab, we will explore mechanics, which is the study of motion and the forces that cause motion. Before beginning any experiment in the laboratory, be sure you are familiar with laboratory safety requirements. For a demonstration of basic lab safety rules, you can watch our video entitled Lab Safety. Much of what we understand about mechanics was discovered by Sir Isaac Newton, an English physicist from the 17th century. He outlined 3 laws of motion. The first law of motion can be stated as: an object at rest will remain at rest, and an object in motion will remain in motion at a constant speed in a straight line unless acted on by external forces. According to the first law of motion, an object at rest will remain at rest unless acted on by an external force. A force is defined as any influence, such as a push or pull, that has the potential to change an object's size, shape, or velocity. An external force could be a hand pushing or pulling an object, or it could be a hammer striking a piece of metal to shape it. It could be gravity pulling an object to the ground, or it could be the results of 2 colliding objects. Force is measured in units called newtons, which were named after Sir Isaac Newton. A newton is the amount of force required to move an object with a mass of 1 kilogram and accelerate it to 1 meter per second squared. For example, if a toy car with a mass of 1.0 kilograms is given a push with a force of 1.0 newtons, the car will accelerate at 1.0 meters per second squared. A force of 1 newton can also be described as the amount of force produced by the weight of an average-sized apple pressing down on a person's hand. To perform experiments with mechanics, we will use a small device called a dynamics cart that rides on a metal track. The cart is specially designed with wheels that produce very little friction. The dynamics cart contains internal sensors that measure its speed, direction, acceleration, and other aspects of motion. The sensor data is displayed on a computer. Let's use the dynamics cart to test the first law of motion. Notice that the cart is at rest and it remains at rest. The cart has no external force acting on it, so it has no velocity or acceleration. It is at rest. The data we are receiving from the cart confirms this. This overly simple demonstration deals with an object at rest. But the first law of motion also deals with objects in motion. In physics, motion is defined as a change in the position or orientation of an object. According to this law, when no external forces are acting on an object in motion, the object remains in motion at a constant speed in a straight line without change. This part of Newton's first law of motion is difficult to demonstrate accurately on Earth because 2 forces, friction and gravity, are always acting on moving objects within the atmosphere. For instance, when a ball is kicked, force is applied to the ball, and the ball travels upward. As the ball moves through the air, it makes contact with air molecules. This contact produces friction, which causes the ball to lose energy. At the same time, gravity pulls down on the ball. As a result of the forces acting on the ball, it will eventually lose speed and fall back to the ground, unless an external force acts on it again. However, in outer space, the first law of motion can be demonstrated more accurately. If a ball is kicked in space, it will continue moving at the same speed in the same direction, and it will continue moving at the same speed in a straight line forever. A force will cause a dynamics cart to move down the track, but it will not continue in motion at a constant speed because the forces of friction and gravity act on it to slow it down. Newton's first law of motion describes an object in motion or an object at rest. Newton's second law of motion describes how an external force affects the motion of an object. It states that the acceleration of an object is directly proportional to the force acting on it and inversely proportional to its mass. The second law of motion can be expressed in the equation acceleration equals force divided by the mass of the object. Average acceleration is the rate at which velocity changes. To calculate average acceleration, divide the change in velocity by the change in time. For example, if an object's velocity increases by 10 meters per second in 4 seconds, its average acceleration is 2.5 meters per second squared. We will use our dynamics cart to perform 5 experiments relating to the second law of motion. For the first 3 experiments, the mass of the cart will remain constant at 0.50 kilograms. For this first experiment, we need a force to accelerate the cart. That force will be produced by this brass weight, which has a mass of 0.20 kilograms. The brass weight hangs on this string, which is attached to the cart. To calculate the amount of force this weight produces, we use the equation force equals mass times the acceleration due to gravity. Acceleration due to gravity is the acceleration an object gains because of the pull of gravity on that object. We already know the mass of the brass weight is 0.20 kilograms. On Earth, the acceleration due to gravity is 9.81 meters per second squared. If we substitute the values for mass and acceleration due to gravity into the force equation, we see that the brass weight produces a force of 2.0 newtons. According to our sensor readings, the acceleration of the cart was 2.5 meters per second squared. From our first experiment, we see that a force of 2.0 newtons produces an acceleration of 2.5 meters per second squared on our dynamics cart. To help us make some comparisons later in this lab, we have recorded the results of this experiment on a table. If the mass of an object remains constant, the second law of motion tells us that the acceleration of an object is directly proportional to the force acting on that object. In other words, if the force increases, acceleration also increases at the same rate. Let's consider the example of a person pushing a stalled automobile. The force applied by the person will cause the automobile to accelerate at a certain rate. If we add another person pushing with the same amount of force, the force is doubled. Since the mass of the automobile remains constant, the acceleration will also double. We increase the force by increasing the weight attached to the string. The new mass is 0.40 kilograms. The increased mass produces a force of 4.0 newtons, which is twice the force that was applied in the first experiment. Let's see how our dynamics cart acts according to the second law of motion. According to our sensor readings, the acceleration of the cart in this experiment was 5.0 meters per second squared. Here is a comparison of the data from our first two experiments with the second law of motion. When the force increased, the acceleration increased proportionally. Now, let's find out what happens when we reduce the amount of force applied to the dynamics cart. We reduce the force by replacing the weights with a single weight, having a mass of only 0.10 kilograms. The new mass of 0.10 kilograms produces a force of 1.0 newtons. Since acceleration is directly proportional to the force, a decrease in force should cause the acceleration to decrease proportionally. Let's see what happens. According to our sensor readings, the acceleration of the cart was 1.25 meters per second squared, which we rounded to 1.3 meters per second squared in this experiment. Let's compare the data from the second and third experiments. When the force decreased from 4.0 newtons to 1.0 newtons, the acceleration decreased proportionally, from 5.0 meters per second squared to 1.3 meters per second squared. Once again, our results show that acceleration is directly proportional to the force. The second law of motion also tells us that acceleration is inversely proportional to the mass of the object if the force remains constant. In other words, when the mass of the object increases, the acceleration decreases, as long as the force remains constant. We will demonstrate this in our next experiment. In our previous three experiments, we used a dynamics cart with a mass of 0.50 kilograms. We now add two more weights to increase the mass of the cart to 0.75 kilograms. The force is the same as it was in the previous experiment, 1.0 newtons. Let's perform our fourth experiment. According to our sensor readings, the acceleration of the cart was 0.67 meters per second squared, which we rounded to 0.7 meters per second squared. For this experiment, we used the same force as the previous experiment, 1.0 newtons, but the increased mass produced less acceleration. Our results show that acceleration is inversely proportional to the mass. We will perform one more experiment with mass and acceleration by decreasing the mass of the dynamics cart. We decrease the mass by removing the weights. The new mass of the cart is 0.25 kilograms. With the same force as before, let's see what happens to the acceleration. According to our readings, the acceleration of the cart was 2.5 meters per second squared. Using the same force as before, 1.0 newtons, but with a decreased mass, the acceleration was greater. Our results show that the acceleration is inversely proportional to the mass. This brings us to Newton's third law of motion, which can be stated as follows. When an object exerts a force on a second object, the second object exerts a force that is equal in magnitude but opposite in direction to the first force. If an object interacts with another object, it applies a force to the second object. This application of force is called an action. When a basketball strikes the floor, it applies an action force to the floor. At the same time, the floor applies a reaction force to the basketball.
The reaction force is equal in magnitude, but opposite in direction to the action force.
The downward action of the basketball hitting the floor produces an upward reaction that causes the basketball to bounce upward. Since an action force often produces motion in one direction, and a reaction force produces motion in the opposite direction, it is important to indicate an object's direction of travel when discussing velocity or acceleration. To indicate direction, we often use terms such as left, right, east, west, up, down, forward, or backward. For example, the velocity of a bicycle traveling at 4.0 meters per second toward the east has a magnitude of 4.0 meters per second and a direction of east. So, its velocity is 4.0 meters per second east. To avoid using words to describe direction, physicists often use a positive value to indicate motion in one direction and a negative value to indicate motion in the opposite direction. The bicycle's velocity would be positive 4.0 meters per second. If the bicycle turned around and traveled 4.0 meters per second toward the west, its velocity would be negative 4.0 meters per second. Earlier, we said that we find the average acceleration by dividing the change in velocity by the change in time. If the velocity of an object increases as it travels in a positive direction to the right, the acceleration will be positive. However, if the velocity increases but in the opposite direction to the left, the acceleration is negative. Negative acceleration is also produced if the velocity of an object decreases or slows down. Let's demonstrate Newton's third law of motion, the law of action and reaction, with our dynamics carts. Each dynamics cart is equipped with a spring-loaded plunger that exerts about 1 Newton of force. For our first experiment with Newton's third law of motion, the plunger from cart A will apply an action force to cart B. Notice what happens when we activate the plunger.
The action force applied by cart A pushed cart B forward.
At the same time, the reaction force of cart B pushed cart A back. Each cart traveled the same distance but in opposite directions. This tells us that the magnitude of the reaction force was equal to the magnitude of the action force, but in the opposite direction. Our sensor readings indicate that each cart accelerated to 2.2 meters per second squared. Cart B accelerated to the right, but cart A accelerated in the opposite direction, to the left. Acceleration is a vector quantity, so its value must express direction as well as magnitude. For this lab, accelerations to the right will be assigned a positive value, and accelerations to the left will be assigned a negative value. So, the acceleration of cart B was positive 2.2 meters per second squared. The acceleration of cart A was negative 2.2 meters per second squared. In this experiment, the mass of cart A was 0.25 kilograms, and its acceleration was negative 2.2 meters per second squared. The mass of cart B was 0.25 kilograms, and its acceleration was positive 2.2 meters per second squared. For our second experiment with the third law of motion, the plunger from cart B will apply an action force to cart A. Notice what happens when we activate the plunger. Both carts behaved exactly as they did before, even though cart B applied the action force and cart A applied the reaction force. The same force acting on two objects with the same mass produces the same rate of acceleration. However, One acceleration is positive and the other negative because the carts traveled in opposite directions. For our third experiment, with the third law of motion, let's see what happens if we increase the mass of one of the carts. We add weight to cart A to give it a mass of 0.75 kilograms. The mass of cart B will remain at 0.25 kilograms. Cart A will provide the action force. Notice what happens when we activate the plunger. Once again, the magnitude of the reaction force was equal to the magnitude of the action force, but in the opposite direction. This time, cart A moved only a short distance and its acceleration was negative 0.8 meters per second squared. Cart B moved the same distance with the same acceleration as it did in experiment 1. A force equal in magnitude but opposite in direction was applied to each cart. However, since cart A had a much greater mass, its acceleration was only slight. For our last experiment, we will increase the mass of cart B and decrease the mass of cart A so that each cart has a mass of 0.50 kilograms. Once again, cart A will provide the action force. Notice what happens when we activate the plunger.
When the button was pressed, the action force applied by cart A pushed cart B forward.
At the same time, the reaction force of cart B pushed cart A back. The acceleration of cart A was negative 1.8 meters per second squared. The acceleration of cart B was positive 1.8 meters per second squared. Again, we see Newton's third law of motion demonstrated. In our next lab, we will use our dynamics carts to demonstrate momentum, which is another principle of motion. At this time, proceed with the corresponding activities.